Welcome to Module 2.1.3. This is a continuation of the hydrologic cycle, and we will be talking about now the water movement through the soil profile and actually making it into our groundwater and our aquifers. So we left off talking about that we want to ensure that we have some sort of cover, some sort of mulch, so that we can increase the movement of, or at least the retention of water in our soil profile. But we need to make sure that we have enough water moving on top of it in order to push that water through the soil profile. So infiltration is going to be the movement of water into the soil profile. Percolation is going to be water movement through the soil profile. And that as that water moves through the soil, the cation exchange capacity and the anion exchange capacity will act as a kind of like a brittle water filter to remove some of those chemicals and contaminants from that, so that by the time it makes it to the aquifer, we have more purified water. So fresh water returning to the aquifer because soil acts as a filter for our soil water. So our percolation loss, remember, this is going to depend on the amount of rainfall and its distribution and how much runoff from soil that we have. Some other important factors are going to be how much evaporation our soil property. So we would expect greater percolation loss in a sandy soil versus a more clay loam soil. And then what type of vegetation is actually grown on that soil. So does this crop that we're growing use a lot of water? Does it have good water use efficiency? Do we need to continuously water this? Are we wasting our time because we're sending it through a medium or our soil profile that is sandy and cannot hold on to the water? So possibly like a golf green. And as I mentioned in the previous module, that our percolation loss is going to be greatest in the winter and the early spring. Like it rains consistently, almost, at least twice a week, during December, January, February, and March, and maybe even getting into April. However, once May comes, when we start planting our summer crops, and we need that rainfall, we don't get as much of it. And that is, ultimately that's because that the atmosphere is warmer and that it can hold more water. So this also goes to, some meteorology that when the water, when the atmosphere is cold, it cannot hold as much water. So it has to drop it as rainfall. All right. So I don't think there's a whole lot of notes to be taken for this module. Or at least for this particular one, but just to give you kind of an idea of like where our water tables might be in relation to our water bodies and our aquifers. And then ultimately we're trying to make sure that we get water to these places. But that if we don't have enough water coming from, we don't have enough rainfall, we can't push that water through the soil profile. So again, water that's held in the water table is as groundwater. For arid regions, those are likely to be thousands of meters deep, like the Ogallala Aquifer possibly, because most of that soil is going to be sandy soils. Again, we're talking Arizona, Utah, New Mexico. There's just not a lot of water in that soil, so we need to have a lot of rainfall to move that water table down. Also, that in those regions, they need irrigation, and so they are beginning to run out of water and have to dig those wells very deep so that they can get to that water. So we have what we call this vadose zone, and the vadose zone just means is the unsaturated soil above the water table. In the next modules, we'll talk about capillary action so that we can have some of this water move up into the soil through capillary action, but it will not make it all the way back to the top because the gravity is actually greater than the capillary action for that water to move up. So here we're looking at where we have our water table, we have a pump or a well that is actually trying to pull out water so that they can irrigate these crops. And so you have to think about how much water needs to, fall through or fall on this area in order to get to this saturated zone or this water table. Some of the things that are going to move into those drainage waters, if we don't have the right soil type, we can actually contaminate those beneath. We'll have these dissolved or solid materials. So this is almost kind of like point source pollution, but we don't really recognize how much is actually flowing into our groundwaters because, it's possibly that it's underneath the soil. We have these containers that are dug deep down so that they don't contaminate our surface waters, but it's even worse because they're actually contaminating our groundwater. So here we might have this factory that has this waste disposal that has these toxic chemicals, and for some reason that ground tank ruptures and it moves into our water table and ultimately contaminates these streams, and people are wondering where the contamination came from. Because everything on the surface, this factory looks like it's doing everything it's supposed to, but we didn't know that there was this, tank that ruptured and is now contaminating our subsurface or our water table. Again, just another look. And so this goes into when we're thinking about how to ensure that these storage tanks beneath the surface don't contaminate our groundwater flow. All right, so some of the problems that we'll have with leaching of our plant nutrients and amendments is going to be eutrophication, and many of us are aware of this. This is going to be the algae blooms. This is going to be it's kind of that green, nasty lich that we see in water that makes us not want to get in it. And so the biggest problem with eutrophication is that it depletes oxygen from the water. And if there's no dissolved oxygen in the water, then our aquatic life struggles and cannot breathe. Even though they have water from the, oxygen from the water, like H2O, there is not enough dissolved oxygen that they can use to perform their metabolic functions. We can have contamination of drinking water, such as nitrates, and I'll definitely address this in when we talk about the nitrogen cycle, because that's a pretty big deal. And we don't want to contaminate our drinking water. So, maybe some of our human wastes, our toxins and pesticide and other wastes, like let's say we have a septic system that fails and that, human waste gets into the water table into the groundwater, the water table. How do you go about cleaning that up? Because the whole entire water table is then contaminated. So those can cause big issues. And then ultimately, as I mentioned before, this gets us into, the Gulf of Mexico and the hypoxia zone. So while we want to have soil water because we need it for our plant growth, we also don't want to have an excess of soil water because then our plants will be waterlogged. So we need to move water off of our land. And some of the ways that we'll do that is with a surface drainage ditch. If you have a large area that needs to be drained, you could do land forming. You can have an open ditch you can have an open ditch drainage system. Possibly in, maybe golf courses, you might want to do drain tiles, or you could do mole drainage. And we'll go over a few of these just to show you some examples here in just a moment. But some of the 5 ways that you could enhance soil drainage is going to be with this surface drainage ditch, land forming. We can have an open ditch, drain tiles, and mole drainage. All right, so you may have seen this around. We've gotten really good with our technology and being able to landform this so that we can move water off of our sites effectively, efficiently, but also not too fast so that we actually get to maintain some of that soil moisture. We have an open ditch. And so, when I'm thinking about this picture in this open ditch, I'm thinking like a football or a soccer field. If you've ever noticed a football, or it's especially a soccer field, because they're much bigger, there's a slight crown down the center of that field such that that water gently moves away from the center off to the sides, and then there will be this drainage ditch that allows that water to move off site. Subsurface drain tiles kind of do the same thing, except that there's going to be some movement into the soil first, and then out, underneath the soil. That water will then move to the closest water body that will receive that water. So we want to try and move that off of our soil very quickly so that we don't have that water kind of pond on top of our production field. And there are several different types. This course is not designed to talk about the different types of drainage, but just to understand that while we want soil in our water, while we want water in our soil, we don't want our soils to be waterlogged. Next, we have mole drainage. And you can see that this is just a tractor that is pulling this pipe, or this bullet that is opening up a channel for this water to flow. However, this is probably not effective because if there's nothing to keep this channel open, then that channel will collapse. And if it collapses, then you're stuck and you have to come back and you have to redo it again anyhow. So mole drainage probably not going to be very good unless you actually had something that was like a pipe, which is basically going to be subsurface drainage, that is going to hold the structure of that channel that you're building. Next, moving into septic tanks and drain fields, I feel like this is kind of where soil science really comes into play, because you are going to be kind of assessing what the water movement through a soil profile is going to be. And if the water doesn't move fast enough, well, then your septic system will back up. If the water moves too fast, then you will not get enough, the water will move too fast through the soil profile, and you won't be able to remove those contaminants or use that soil as a filter. So inside of a septic system, we're going to have our sewer come in. There are different types of septic systems, but for the most part, it is going to sit there and maybe go through some baffles that kind of allow that stuff to settle. You'll have different microbes that are in there that are going to decompose some of these materials and kind of change what they are. And then eventually that wastewater will come out into the drain field. And so this is where soil scientists will come in and do perk tests, and they'll make sure that the water is moving at least that it's moving into the soil profile, but making sure that it doesn't move through so fast through the soil that some of those contaminants are not removed. So septic systems are important. There are about 10 million households that have septic systems. And that's kind of one of the important roles of soil, is to filter some of that effluent or some of that waste so that, it's out of sight, out of mind. It reduces contact with people. It doesn't necessarily require the energy that is needed if you were to send that to like a municipal waste treatment system. So as I mentioned before, there are going to be a PERC test, or what we call saturated hydraulic conductivity. and how much that water can hold, what is the microbial activity, how much CEC or AEC that you have in order to kind of attract those anions or cations, and then ultimately that you'll be given a suitability rating. And you can find some of these actually in Web Soil Survey, just to get a good idea or a quick idea as to if you will be able to use this soil to put a septic system in there or not. All right, so that is the movement of like our waste. Some of the other things that we want to think about is how much water we're applying through irrigation. So, one of the biggest problems that you'll probably see is, some homeowner that is trying to irrigate their lawn, and sometimes their sprinklers are not appropriately set, and they're also watering the concrete or the pavement. And as if we are not in enough water crisis, we don't need to just be watering lawns just for the sake of watering lawns. And if we are going to water them, let's make sure that we keep the water on the lawn and put just enough to keep our plants growing. We don't necessarily need to saturate or to overwater our areas. This is going to be a big issue because food production is where we use most of our water. So up at Oakley, we have a hydroponic tomato production facility, and we are trying to do this, at least doing hydroponics, we can recycle some of that water. But growing crops in, just out in the open, given our, current climate situation, we're going to need to apply irrigation. And we're going to need water for at least 40% of our global crop production. So how do we produce more food without water? Is going to be a big deal, and plants can't grow without water. So water use efficiency is going to be a big thing as we move into the future. We're definitely overpumping our aquifers because we need that water in order to irrigate our crops. And so because we're overpumping those aquifers, we're having these falling water tables. We cannot hold as much in our existing reservoirs. And we also need to recognize that a portion of our river flows are needed for freshwater habitat rather than for growing crops. So we're running into where do we get the water from in order to increase this crop production and this nutrient uptake. So we're being asked to do more with less. Pretty much, how do you grow crops without fertilizer and water, which are two of the main components that you need in order to grow crops. So when we look at water efficiency, what is the water application efficiency? How much is actually supplied to the roots? Do we want to over apply water? How much is actually being taken up by the roots? Our field water efficiency is about 50 to 60%. And so this is going to be actually our transpiration ratio. So all of these things are going to come into play. You'll probably get a little more exposed to these if you were to move into a crop production system where you need to worry about how much water you're actually supplying to them. At some point in time, I do believe that they are going to start charging us more for our water so that we become more effective and efficient with it. Here's just a look at some of the pivot irrigation. This is common. You'll see that it is more efficient to have this period irrigation system that is going to apply this circle or maybe even a half circle. We are more efficient with our water than if we were to apply some sort of blanket irrigation or consistent irrigation across this whole area. We don't see a lot of this here, but you will see a lot of this out in the Midwest. We see a lot of this in the Delta where there are, extensive crop production and needing this irrigation because that crop is actually valuable. And so here's a look at a full irrigation system, a pivot irrigation system. And so as we're seeking to become more effective and efficient with our water, we now have variable rate pivot irrigation, where some of these nozzles will increase or decrease the flow of water based on moisture sensors that are located in this field. So that if there was a moisture sensor here that said we don't need any water. By the time this irrigation, by this section of this pivot irrigation reached that sensor, it would turn off. So we're trying to do things that are helping us become more efficient, just not necessarily sure how great we are going to be at that. So some of the things that we're also looking at, and I want to talk about when I think about crop yield and what we need to do. So the difference between maximizing the crop yield and maximizing profit. So in module 3, we'll talk about the law of diminishing returns. And at some point, you're wasting time, you're wasting money, you're wasting resources by trying to apply more water. The plant can only take up so much water. It can only take up so much nutrient. It can only utilize so much nutrient. So applying more doesn't necessarily equal greater crop yield. And so what this graphic is showing is that, in order to maximize the crop yield, we need about 190 millimeters of water. However, to maximize the profit, because the plant will still grow to a certain point, like we're not getting much more growth and we're giving up our growth for our profit. And so these are going to be some of the things, these are going to be real good jobs in the future if you can understand how to maximize the profit and become more efficient with your water use. And I don't really like using the term maximize. I like using the term optimize, because there's a balance between the amount of water that you need and the amount of nutrient that you use in order to optimize yield so that you are actually winning at the bank rather than winning at, winning at the diner or at the grain bin or wherever you're selling your crop at. Drip irrigation is going to be something that we'll use, especially for our high value crops. This is expensive to install, but it's also the most effective for our high value crops, strawberries, blueberries, things of that nature, because we're going to get the return on investment by being efficient with our water systems. You might see drip irrigation with a lot of hoses, micro irrigation lines. So we're only applying water where that plant is growing. So we're only putting water right here. This plant doesn't have to work very hard in order to get the water that it needs. It's already supplied. And we can also apply this consistently and periodically throughout a day to make sure that the plant is never stressed. All right, so wrapping this up, some of the things to be aware of are the different irrigation type, different irrigation methods. In the Mississippi Delta, you've got, probably a 1 mile field that has been graded, and it'd be very difficult to apply water to those row crops over a mile distance. But if you have a conventional furrow, that water will travel down and out the end, and you can get about 60% efficiency. So this is more time and cost effective rather than it is, good for water efficiency. Our drip irrigation is going to be the greatest. However, it also costs the most in order to apply. So there's going to be this trade-off between efficiency and cost. We would not want to do drip irrigation on, a 400-acre cotton field. That just wouldn't make sense. All right, so that's going to end module 2.1.3. We have one more module, which is going to be 2.1.4, and that is really going to be talking about how soil water is held and how it moves.